X month after the device was released. So X is in months. Time in months. Find the point of inflection and interpret its meaning in terms of the rate of change in sales. Very interesting and very important type of question. So I'm going to write the question here for us to have it. So we're asked to find the inflection point, and we're asked to find or write, interpret it in terms of the rate of change of sales. In sales, I should write. Okay? So find the inflection point and interpret what that means. When it comes to the rate of change, the inflection point deals with which derivative?
Second.
Yes, thank you very much. We can never jump over the first, so we have to find the first derivative first. Okay, so let's do it. So S prime will be the rate of change in sales. This is S prime. Okay, so remember how we do it. We bring down 3, so negative 0.0393x squared plus. I bring down 2, let's see what we get. So 2 and 2 and 3 and 1. Correct me if I'm wrong, please. All the numbers, make sure. Negative 2.021. So this is the function that gives the rate of change in sales. Okay, now because we are asked to find the inflection point, we will continue with the second derivative. Any questions on the first derivative? Okay, then I bring down 2, negative point. So this is 6, 8 and 1, 6, 7, 0. Correct my numbers anytime, please. Plus 1.322. Okay, so I have the first derivative, I have the second derivative. I'm asked to find the inflection point. What do I do next? Since the second derivative is always defined, how do I find the inflection point? What do I have to do next? Anyone?
Would you create the table?
Careful. Very good point, but we can. But what I'm asked to determine is, first of all, the inflection point.
Would you set it equal to 0?
Yes, I have to. That's my first step. Next. So I set it equal to 0. This is a linear equation. So I will move 1.322 and divide by this. So of course, X is in months, right? So careful, we have to get a positive number. Make sure that this is clear. So then X will be 1.322 over 0.0786. So I'm going to share my screen, and I'm just going to punch it in. 1.322 divided by 0.0786. Okay, so I got roughly 16.8. So X is approximately 16.8 months. Now, yes, at least I have to show that the second derivative changes sign here. Okay, so this is very important to understand. So X indeed. So it's months. So 0 to infinity, of course, we're not talking about infinity. So we want 16.8 in here. And we want S prime. And we want S of X. And we want the second derivative. And the second derivative is 0 at that point. I would like to determine and make sure that the sign changes here from negative to positive or positive to negative. And then in order to find the inflection point, I have to plug in the function, this value. Okay, so x and y. So go back to y equals. Thank goodness we finished with this function. It was really ugly. Okay, so negative 0.0131 x cubed. No, I didn't mean that. Where did it go? Okay, then plus 0.661 x squared, and then minus 2.021x, and then plus 6.865. And then second in table, and I need 16.8. And that's the sales in millions of units. Okay, so I got 97.36. So 97.36. So then I know that this is the inflection point, only if the sign changes. Okay, so let's look at the second derivative. The second derivative is a linear function. You don't need to plug in anything in a linear function because when the leading coefficient or the slope is negative, the function looks like this. It has to come from positive and go to negative. But let's say we don't notice that. Let's plug in 0. If I plug in 0, what is the sign of the answer? I just care about the sign. I don't care about the number. Of course, as expected, positive and negative. This is the sign of the second derivative. So now this is guaranteed to be an inflection point. What is the inflection point again? 16.8, comma, 97.36. Okay, so we found the inflection point. It is an inflection point because the second derivative changes sign. So the function here opens downward or does opens upward or holds water. It does not hold water or opens downward. Now, let's talk about the interpretation. What does this mean for the rate of change? So what does the inflection point mean for the first derivative? That's what it means. That's what the problem is asking us. Interpret the inflection point in terms of the rate of change in sales. So this is basically the same thing with assuming that we know, I don't want to look at the first derivative. I don't want to look at the function actually, not the first derivative, sorry. So if this is the function, this is its derivative. So what type of point will this be for this function? Positive and negative. As if this, yes, what type of point? 16.8 comma 97.36 will represent for the first derivative. For the function, we know it's an inflection point. It's carved in stone. But what does the inflection point represent for the first derivative based on the sign change of positive to negative? What do you think?
Is it a max?
Exactly. This is a max or gives a max rate of change of sales. I still write O for some reason, but it's in sales. That's exactly it. What if we had minus positive here? What would you have concluded this particular inflection point would have been for the rate of change in sales? What would you have concluded if the signs were reversed?
It will be a
A
minimum.
myth.
Exactly. Perfect. Okay, in the next section, we're going to put everything together and we are going to graph. So this section mainly deals with rational functions. Rational functions, I think, are much easier to handle than those exponentials that we looked at the beginning tonight to finish it up. Any questions for me before we continue? I'm just going to entitle this graphing. So finally, we are ready to do that. Now, this particular section, as I mentioned, deals with rational functions. And we're only going to look at 3 different types. There are more than 3 types of rational functions. This one, type 1, I like to call it type 1. Nobody calls them type 1. You don't have to call them anything. Is a situation like this. In which the degrees are the same. It could be 2, it could be 3, it could be 1 and 1, but same degree. So this is type 1, same degree. Numerator and denominator have same degree. Type 2, the easiest of all, when the degree in the denominator is bigger. So bigger, higher degree in the denominator. This is the easiest. And the most difficult one is number 3, in which the numerator has a higher degree than the denominator, but by exactly 1 unit. Exactly 1 unit. Something like x cubed over x squared minus 1. 1 degree higher. So rational functions that we are going to look at come from these 3 types. Type 1, same degree over same degree, not a big deal. Type 2, the easiest. Type 3, the most difficult. And you'll see in a minute why. So let's start with these, and then we'll look at the graphing other types of functions. So this is the major issue here. Putting everything together to graph the function. Okay, so I'm going to choose a few examples in which we talk about asymptotes first. No graphing at the beginning. So let me talk in general about asymptotes. They are of 2 types. Vertical, horizontal. Actually 3, and slant. This is typical to number 3, only. This is only number 3. I didn't want to talk about it right now, but I just want you to have all types in one spot. We're not going to talk about this right now. We're going to talk about these 2, and then I'll come back when we'll talk about this one only for type 3. Because type 1 and type 2 will not have slant. Only type 3. Only type 3. Okay, so let's leave it alone. Okay, so what is a vertical asymptote? So here is an example of a function with a vertical asymptote. You know all this, but let me emphasize it. it's not part of the graph. It will not be graphed as a solid line. It will be graphed as a dashed line. And the function left and right cannot do both, right? So on this side could go to infinity. On this side could go to infinity. On this side could go to negative infinity. So there are 4 combinations, 4 possibilities, both to positive infinity, both to negative infinity, 1 to positive, 1 to negative, 1 to negative, 1 to positive. So there are 4 possibilities. So if this is x equals a, any number you want, then we will have to determine the limit as x approaches a from the left of the function, and of course the limit as x approaches a from the right of the function. So it's not sufficient to say, oh, I know x equals a is a vertical asymptote. We also have to determine these 2 limits. In my example here, this first limit from the left is infinity, and the right limit is negative infinity. That's all there is about vertical asymptotes. What about horizontal asymptotes and how we determine them? So let's look at an example first. So here's a potential horizontal asymptote, not part of the graph, not a solid line. So let's say y equals a. And what could the function do? Let's say it does this, approaching, getting closer and closer, closer and closer to a. And let's say on this side, it does this, getting closer and closer to a as x approaches negative infinity and then x approaches positive infinity. Totally different situation. Here we are talking about the limits left and right, but here we're talking about the limits as x approaches negative infinity and as x approaches infinity, and we have to determine those limits. So I have to find the limit as x approaches infinity of the function and the limit as x approaches negative infinity of the function. In my example, they're both a. Therefore, y equals a is a horizontal asymptote. And leave this one alone before we will get to it when we get to slant asymptotes. I will not require you on a test to graph one. I will show one. You may have homework, but this will not be for tests or final exam. Too long of a problem. I may just ask you to find the slant asymptote, but not to graph the whole thing. Okay? So let's look at a simple example. Let's start with a type 1. I really want to find the asymptotes first for one problem or two, and then, okay. So here it is. So we have f of x equals 6x squared plus 4x over 3x squared minus x. So we're asked to find vertical and horizontal. Do I know that it doesn't have slant? Of course, because it's same degree over same degree, so this is type 1. If it's type 1, it cannot have a slant asymptote. Only type 3 has a slant. It doesn't have to have vertical, but it will definitely, both these will have horizontal. Okay, so let's take a look.